Welcome to lecture 4.5, Cardinality and Infinite Sets. This is a really fun lecture. I think you're going to like it. We're going to talk about different sizes of infinity, an infinite hotel with an infinite football team, and a famous mathematical problem which was proven to be undecidable. Let's get started. In the previous lecture on functions, I posed the question, what does it mean for two sets to have the same size? Now I answered it, but in this lecture we're really going to explore that. Of course, this is easy if the sets are finite. We just count the number of elements and see if they're the same or not. If the sets are infinite, then things are harder. So I'm going to give you a list of sets, starting with the positive even numbers, integers that is, and then I'm going to keep adding elements to this set to get seemingly larger and larger sets, but then I'm going to ask you which of these are secretly the same size and which ones are not. And that's something that we're going to answer in this lecture. So starting with the positive even numbers, our next set is the positive integers. There are, in some sense, twice as many positive integers as there are positive even numbers. So you could make the case that that's a bigger set, but you could also make the case that 2 times infinity is equal to infinity, so they're the same size. We'll see later which one of these turns out to be mathematically sound. Next, instead of doubling our set, let's add a single number, namely 0 to it, to get the non-negative integers. And once again, I prefer to denote this set just with n, even though some people use n to denote the positive integers. Next up, we have the ordinary integers, which you can think of as basically twice as big as the non-negative integers. Jury is still out as to whether or not these sets have the same size. Next up, we have the rational numbers, which is the set of all fractions, a over b, where b is non-zero, and either a is 0 or the GCD of a and b is equal to 1. So going from the non-negative integers to the integers, we're basically doubling the size. But going from the integers to the rational numbers, we're basically squaring the size, because now we have ordered pairs instead of just single numbers. Although there is some intricacies here, because we get things like 1/2 equals 2/4, 2/4 equals 3/6, and so forth. But it's definitely a lot bigger of a jump, seemingly, to go from the integers to the rationals than it is to go from the non-negative integers to the integers. After that, we have the real numbers. So this includes irrational numbers such as square root of 2, e, pi, and any decimal that does not repeat. Finally, we have the set of all real-valued functions, that is, functions from R to R, and there's no real standard notation for this, so I'm just going to call this script f. And I should mention that this maybe is the odd one out, because everything above is a collection of numbers, and this is a collection of functions. But that said, for every real number, so for all real numbers R, there exists a function, let me call it fr, that goes from R to R. That's just fr of x is the constant function r for all x. So in some sense, the set of all real-valued functions extends the set of all numbers, because for every real number there is a constant function, but then there's a whole lot more things in there as well. Any function that is not constant. And we're not just talking about continuous or piecewise functions. There are some real crazy functions out there. Clearly, we have the following chain of strict containments, as the positive even integers is strictly contained in the positive integers, which is strictly contained in the non-negative integers, which is strictly contained in the integers, and then the rationals and the reals, and then finally the real-valued functions, assuming that we are associating the constant functions with real numbers. But let me ask you, do any of these sets actually have the same size? And if so, what does that mean? So we do know that, again, infinity plus 1 equals infinity in some sense. So does that mean that if we start with the positive integers and we add one number to get to the natural numbers, we get the same size. Now, for finite sets, if A is a strict subset of B, then the size of A is strictly less than B, size of B, if A and B are finite. But as we'll see, that's not necessarily the case for infinite sets. That says, I've said it before and I'll say it again as a spoiler, there are infinities of different sizes. Not all of these are the same size of infinity, but to figure out what that is, we need a formal definition. Let's recall some definitions of functions that we saw in the previous lecture, though I will add a few things to them. So if f is a function from x to y, then f is injective or one-to-one if f of x equals f of y implies x equals y. So that means that we can never have two things in x that get mapped to the same thing. That is impossible. So the way to think of what injective means, or one-to-one, is that distinct elements in the domain get mapped to distinct elements in the codomain. So we use injective sometimes and one-to-one other times. I prefer one-to-one, but it is nice to say things like, let f be an injection. I can turn this into a noun much easier than I can turning that into a noun. Next, f is surjective or onto if it's a slightly different definition than I gave last time, but I did mention this being equivalent. Basically, it means everything gets hit. So if we have y here and we have x here, that means everything in the codomain comes from somewhere, at least one place in the domain. So for all y in the codomain, there exists an x such that f of x equals y. Now remember in the previous lecture I said my definition of surjective or onto was that f of the entire domain was the entire codomain. And that's nice and short and elegant, but as we saw at the end of that lecture when we were trying to prove things, the pointwise definition was more useful. Finally, f is bijective if it is both one-to-one and onto. Let me pause to say a few remarks about notation that you might see elsewhere. I don't think I will use it much, if at all, in this class, and not because I don't like it, but just because I don't think it's really going to come up that much. But something that you should know. So if we want to write down a function, we usually write, say, f, colon, and then an arrow from x to y. If we want to specify or emphasize that f is one-to-one, then we can, not required, put a little hook in the beginning of this arrow like this. So whenever you see this, you can think that the function is one-to-one. We say that f is embedding x. Sometimes we say into y, as opposed to onto, which is surjective. Similarly, if we want to specifically emphasize that f is surjective, then we can put a little double arrow tip like this to mean onto. And of course, we can use both. If it's bijective, we can use both a hook and a double arrow. I don't see that as much, but it's definitely used. Now, if f is bijective, something that I said last lecture, but I want to emphasize, that really means that there's a one-to-one correspondence between elements in x and elements in y. So everything in x has a corresponding buddy in y. So everyone can stick out and shake their hand, and vice versa. So this really means that there are the same number of elements in x and y. When f is bijective, of course, we can define its inverse function. If a is buddies with b, then b is buddies with a. And I did this in the last lecture. Now remember that f inverse of y equals x if and only if f of x equals y. You probably saw this in grade school in like pre-calculus and calculus. Finally, here is the definition that I mentioned in the previous lecture, but I promised to take a deeper dive in this lecture. So two sets have the same cardinality if and only if there exists a bijection from x to y. So the way to think about this is if everyone in x can reach out and find a buddy in y, so nobody is left over, then the two sets have the same size. So let's, as an example, consider the natural numbers. So suppose x is the natural numbers, and let me not include 0. And suppose y is the natural numbers, and let's include 0. So 1, 2, 3, 4, 5, 6. So, and this is 0, 1, 2, 3, 4, 5, 6, etc. So I should emphasize that just because we don't have a bijection doesn't mean that there isn't one. For example, we could do a naive thing. We could say, oh, let's have everyone in X reach out and find the guy with the same name tag. So 2 shakes 2's hand, 3 shakes 3's hand, and so forth. And if we do this, this function is not bijective because 0 doesn't have a buddy. So that does not mean that there is no bijection. It just means that what we have isn't one. So of course we could get smarter and we could say, oh, everybody in X person n should shake the hands of person n minus 1, and then we get a bijection. And so this is why these two sets have the same size, even though X is a proper subset of Y. And that makes sense because these two sets, so here's the natural numbers, the positive naturals, and here are the natural numbers. And if you look at the dots and you just erase just throw away the name tags, get rid of those name tags and those name tags, the sets are the same. It's just this infinite line of dots. The fact that we labeled them differently doesn't change the underlying sets. The fact that we can label them with the positive naturals means that this is the positive naturals, and same with the regular naturals, but they still have the same size because there is a bijection between the two.
Hopefully you understood and agreed with my previous example of how we had two sets. One was a proper subset of another, but they were the same size. And the moral here is that infinity doesn't behave like things do in the finite world. We can't just add infinities willy-nilly and get results that make sense. But that said, sometimes we can, or at least sometimes there are ways to formalize things, but that's way beyond the scope of this class. So what I want to do is show you a bunch of equations and ask you what the answer should be. And should is in quotes because I'm lying. So what about 1 plus infinity? Well, we saw that if we took the positive natural numbers and we added an element to it, we still got, so the size of the positive natural numbers with one extra element is infinity, and that's the same as the size of the positive natural numbers by itself. So that's going to be infinity. 1 divided by infinity, hopefully you agree, is 0. And, again, formally I could write this as the limit as n goes to infinity of 1 over n is 0. But let's not do that for now. Let's just try to understand these intuitively. Infinity divided by 1, hopefully you agree that that is infinity. 0 divided by infinity, well, hopefully you agree that that is 0, because 0 divided by any number is 0, and infinity is, in some sense, bigger than any number. 2 times infinity, that seems like that should be infinity, because here we have the size of the integers, which is, in some sense, 2 times the size of the natural numbers. Now, are these the same infinity? That's something that we'll explore soon. Infinity times infinity, well, that can't be finite. It also has to be infinity, but it's not clear whether a set. So here I'm asking, what about the set of what about the rational numbers versus, say, the natural numbers? Are these the same size? They're both infinite. Infinity minus infinity, well, there we could get into trouble because, are we taking the integers and subtracting off the natural numbers? If we do that, we get a set of infinite size, or are we taking the natural numbers and subtracting off the positive natural numbers, in which case we get a set of size 1. Or if we take the integers and subtract off the entire integers, we get something of size 0. So this is not going to be well defined. What about infinity minus 1/4 infinity? Could that possibly be infinity? Because this is definitely in some sense smaller, I claim that that's not going to be well defined either, and I'll show you an example really shortly about why that doesn't work. Let's do that with a thought experiment. Suppose farmer A plants a seed every day, but every fourth day a bird comes along and eats the seed he just planted. Moreover, suppose there's a farmer B who also plants a seed every day, and every fourth day a bird comes by and eats a seed, but this bird eats the first seed he planted. Which farmer has more plants remaining at the end of time? It's in quotes because I'm lying. That doesn't really make sense at the end of time. And we're assuming that the plants live forever. Also doesn't make a lot of sense. So let's see. So farmer A plants a seed every day, and on the fourth day, the bird eats the fourth seed. On the eighth day, the bird eats the eighth seed. On the 12th day, the bird eats the 12th seed, and so forth. Whereas farmer B, so day 1 this gets eaten, on day 4 this gets eaten, on day 8 this gets eaten, and on day 12. For farmer B, on day 4 the first seed gets eaten. On day 8 the second seed gets eaten. And on day 12 the third seed gets eaten, and so forth. So at the end of time, granted something that doesn't make sense, farmer B doesn't have any seeds remaining. Every single seed that farmer B plants gets eaten. So in this case, infinity minus 1/4 infinity equals 0. That's what I asked you up here. However, for farmer A, there are infinitely many seeds that remain. Or I should say now there are probably plants. So infinity minus 1/4 infinity in this case is going to be equal to infinity. So that's why you can't really treat infinity, that's not why, but this is one of many reasons why you can't treat infinity like regular numbers. It's not just what you're subtracting, but it's how you're subtracting these things. Let's do another thought experiment. This one is quite well known, and it was proposed by mathematician David Hilbert in 1924. I think we talked about David Hilbert earlier. He tried to axiomize geometry in the early 1900s. In this scenario, there's a hotel, sometimes called Hilbert's Hotel, that has infinitely many rooms, but no vacancies. However, the manager is able to shuffle people around to open up a room if needed. Here's a picture of the hotel. So it's one of those motel styles that just has a big line of rooms. So suppose the hotel is full. So every room is occupied. Let's think about what the manager can do to accommodate the following situations. First of all, suppose that a single person shows up wanting a room. So what happens? Again, there's no vacancies, but the manager can get on the loudspeaker and say, everybody, I need you to move to the next room. So person 1 moves to room 2, person in room 2 moves to room 3, person in room 3 moves to room 4, and so forth. And what's going to happen is that room 1 will open up, and our new traveler gets a room. So in this case, this is like saying that infinity plus, or 1 plus infinity equals infinity. Okay, that's simple enough. And you can imagine that if 10 people show up, you can do a similar trick, but now everybody gets to move 10 rooms ahead instead of just 1 room ahead, and so forth. So this says that 10 plus infinity is equal to infinity. And I really should put this in quotes because I'm technically lying. Though, that said, there are ways to formalize things like this under certain circumstances. Now, what if instead of 10 people show up, what if there's an infinite bus with infinitely many people who show up? And I'm going to say that they're a football team because maybe every person is wearing a jersey and every integer appears on some jersey. That just makes it easy to number the people. So now there are no vacancies, and we have infinitely many people with jerseys, 1, 2, 3, 4, etc., who show up and they want a room. So what does the manager do? Well, the manager can get on the loudspeaker and say, well, I want everybody to move into the room that is double your room number. So person 1 moves into room 2. Person 2 moves into room 4. Person in room 3 moves into room 6. The person in room 4 moves into room 8. The person in room 5 moves into room 10. The person in room 6 moves into room 12. And this opens up the odd rooms. So now you take football player 1, put him in room 1. Football player 2, put him in room 2. Football player 3, put him in room 3. Football player 4, put him in room 4. And so forth. We keep doing this, and everybody gets a room. Now, if we have a second infinite football team that shows up, we can do the same trick. So this first one says infinity plus infinity equals infinity. And well, the second one doesn't say anything different. We just can keep doing that. But now things get harder. Suppose a bigger bus pulls up and another football team walks out, but this one is bigger than the last two. For this one, all of them have jerseys, see if I can draw this, with a fraction. So like 2/3. There's a football player with that jersey number. And let's just say positive integers. So I'm going to call this the rational or the positive rational number football team, and they want a room. So it's not clear at all whether they can fit in this one-story motel, because once again, the rational numbers are of the form P over Q. So think of this as ordered pairs, P comma Q under some equivalence. So it's almost like this is you would need a two-dimensional hotel. It seems like it. So an infinite number of rooms on the first story and the second story and the third story and infinitely many stories. Is there a better way? So think about that. Before we answer that, let me give you something even harder. Suppose the real number football team shows up wanting rooms. So now we have we have some football player that has, now I really can't draw jerseys, but it has pi on it, or E, or something that we can't even comprehend. Well, let me tell you the answer. So when the rational number football team shows up, the manager gets on the speaker and says, okay, I need everybody to do the same thing that you just did. Go into the room that's double your room number. So 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8, 5 goes to 10, 6 goes to 12, and so forth, leaving open the odd-numbered rooms. And the manager has a plan for how to fit this rational number football team into these odd rooms. And I'll show you that on the next slide. But that said, when this next bus pulls up, the real number football team, the manager gets on the speaker and says, I'm sorry, we can't fit you. We have no vacancy. And that I will show you in a couple slides as well. Now, let me clarify what I'm really saying by this thought experiment is the rational numbers has the same cardinality as the natural numbers. Those two sets have the same size. So the rationals have the same size as the natural numbers. And by the second statement saying you can't fit the real numbers in the hotel, by that I'm saying that the cardinality of the real numbers is strictly bigger than the cardinality of the natural numbers. Let's start with the cardinality of the rationals. So suppose we have a bus containing, this time I'll clarify, the positive rational number football team. And they show up to Hilbert's hotel, and let's just assume it's empty to make things easier. How could the manager assign room numbers? So here's what he does. He takes out a sheet of paper, of course an infinite sheet of paper, and writes down this grid right here. Now, of course, there's going to be some redundancy. So the person with jersey number 1 is represented as 1 over 1 and as 2 over 2, 3 over 3, 4 over 4, and so forth. But the manager doesn't really care about this. The manager takes out a pen and starts at the bottom left corner and says, that's person number 1, you go in room 1. And then he takes his pen and he does this little thing. So he does this little zigzag path through the rational numbers. And he goes through, and every time he encounters a rational number that he has not seen before, he says, okay, calls out that person's jersey number and say, you go in the next room. So 1/2 goes in room 2. 2, person number 2, football player with jersey 2 goes in room 3. Person with jersey number 3 goes in room 4. Let's see, we've seen 2 over 2, so let's ignore that. 1/3 goes in room 5. 1/4 goes in room 6. 2/3 goes in room 7. 3/2 goes in room 8. 3/2. 4 goes in room 9. 5 goes in room 10. 4/2, we've seen that. So let's ignore that. 3 over 3, we've seen that. 2 over 4, we've already seen that. He's in room 2. 1/5, he's in room 11, and so forth. So what we are doing is we are constructing a bijection. This assignment of room numbers to rational numbers, positive rational numbers, is a bijection from the positive natural numbers to the positive rational numbers. Or you can go backwards. If you want to think of it as a function that goes from the positive rationals to positive natural numbers, well, that works as well. I'll call that one f inverse. However you want to do it, this function, this assignment, is a bijection. If you squint your eyes, what you have in both cases is this row of either rooms or row of people. You got a row of dots, and the first one happens to be the positive rationals. The second one happens to be the natural numbers. They are in bijection with each other. Those two sets have the same size. I just showed you how you can fit the rational numbers into Hilbert's hotel, well, technically the positive rationals. And now I want to show you why you cannot fit the real numbers in. We can formalize this by saying the cardinality of the real numbers is strictly bigger than the cardinality of the rationals. Now, I haven't defined what it means for cardinality to be strictly bigger than. I just said what it means for them to be different, but I think it should be clear that that means that there is no surjection from the smaller set onto the bigger set. So this is something that was proven by Georg Cantor in 1891, and the method is really slick, and it's called Cantor's diagonal argument, which is confusing because the last slide we saw another diagonal argument. We went diagonally through the rational numbers. We snaked through it to construct a bijection. Okay, let's get started. We'll actually prove something easier. We'll take a small chunk out of the real numbers, namely the real numbers whose decimal representation starts with a 0, goes between 0 and 1, and I'll show that that set is strictly bigger than the natural numbers. And that suffices because that set is at least as big as the real numbers, and the natural numbers are equal to the size of the rationals. We'll do this by contradiction. Suppose that there was a bijection from the natural numbers to the interval 0, 1. Let's make a table or a complete list of these numbers. I'll do it vertically. So I could do this notationally. I could say like 0.A11, A12, A13 or something like that. I'm not going to do that. I'm just going to write it out as an example. And I think it should be clear how it generalizes. So let's suppose that, well, I should really start n equals 0. That the first one is 0.8321779439, etc. Say that the next one, n equals 1. So that's f of 0. Suppose f of 1 is 0.914437824141. Suppose the n equals 2, 1 is 0.14118223148. Suppose the n equals 3, 1 is 0.26636148992, etc. Suppose n equals 4. So these things are all decimals. 0.10. I haven't had any zeros in here. Let's change that. 0.1604012, etc. So just suppose that we have this infinite list. Here's what I'm going to do. I'm going to go through and I'm going to circle. In the first entry, I'm going to circle the first, I guess this is the tens digit. Then I'll circle the hundreds digit, the thousandth digit, and so forth. I'm going to just keep circling. I'm going to circle the nth digit in the nth row. And I'm not really worried if I'm off by 1. Just I'm going to go diagonally. That's the diagonal argument, like this. And now here's what I'm going to do. I'm going to write a new number. And here's how I'm going to write it. So my new number is going to be, let's call it x equals 0. So I'm going to take each circled digit and I'm going to just add 1 to it. So I'm going to 0.9. Then the tens digit is 9. It's 1 plus this. The hundreds digit is 2. It's 1 more than 1. So 0.92. Another 2. And then let's take 8, add 1 to it. We get 9 again. Let's take 6, we add 1 to it, and it's 7, and we keep doing this. So we're taking the circled digits and increasing them by 1. And I claim that this number here is not on this list anywhere. And why is that? Well, because it differs from every single number in at least one digit. So it's not this first number because they differ in a digit, a 9 versus an 8. It's not this second number because the 2 is different than a 1. It's not this third number because the 2 is different than a 1. It's not this fourth number because the 9 is different than an 8, and so on. So this number that I constructed is not on the list below. So what does that mean? That means, i.e., x is not equal to f of n for any n, which means that our function f is not onto. And there is our contradiction, and that completes the proof. So I missed a few sentences. I didn't, I think I said, everything I wrote down and said was the proof, but I didn't write down some of the sentences at the end, and I'll let you do that if you want to as an exercise, but hopefully this is a convincing argument and you can see where I arrived at a contradiction. Okay, so again, to summarize, we assumed that there was a bijection between these two sets, and then said if there is a bijection, we can enumerate everything in the image in a list. So I did that, and then I specifically cooked up a number that is not on that list, contradicting the fact that we had a bijection to begin with. It's my hope that you've been going through this lecture and each slide is more and more fun. After a few definitions, we got into farmers and birds, and then we got into Hilbert's hotel, and then we used a clever diagonal argument to show why we can fit the rational football team into Hilbert's hotel, and then we used a very different diagonal argument by Georg Cantor in 1891 to show why we cannot fit the real numbers into the hotel. And now we're going to get even more fun in the last two slides, or at least in my opinion we are. I hope you agree. So this slide, I'll give you the punchline. There are infinitely many infinities. And it's actually so much more cool than that. I just can't get into it in this class. So when you're thinking about this, you're probably thinking that there's like, I don't know, an infinity 1, which is our regular infinity, an infinity 2, an infinity 3, an infinity 4. But no, there are so many more infinities than just an infinite list. But I will just show you how to construct an infinite list of infinities on this slide. Take a class on set theory or go read a book if you want to know more. Here, I will prove the following theorem. For any set A, finite or infinite, the power set of A is strictly bigger than A. In other words, there is not a bijection between a set and its power set. Now, I'm going to claim that this is clearly true for finite sets, right? Because we know that 2 to the n is bigger than n for all natural numbers n starting at 0. Now let's prove it for the non-trivial case when A is infinite. So it suffices to show that there is no surjection from a set to its power set. Now to show there's no bijection, we just have to show that there's no surjection. And by the way, I've said this before, but this is why I like terms like injective and surjective, because we can easily turn them into nouns. Even though I like onto a lot, there's not a great way to make the word onto into a noun. I could say there's no onto function, but that sounds a little bit awkward. Okay, let's do this. It's tempting to do a contradiction, assume that there was one, and break the universe somehow. But I'm not going to do that. I'm going to do it in a more straightforward manner. Let's suppose that we have any old function from a set to its power set. I'm going to just show you that it can't be onto, because I'm going to show you a set that does not get hit. So in other words, it's something that is not in the image. And here's how I'm going to do that. I will define the following set. So let's let D be the set of elements in A with the following property. A is not in F of A. So that's a subset. In other words, it's an element in the codomain. And I'm going to show you that it's not in the image. So let's think about this for a moment, because this is one of those things that might remind you of Russell's paradox. It's this collection of all elements that are not in the image of themselves. But it's not a paradox. This is a well-founded set. There's no reason why this set cannot exist. And think about why that is. So an element I'm going to call, say, A1, gets mapped to a set F of A1. I can ask, is A1 in F of A1? And this is a yes or no question. Similarly, A2 gets mapped to F of A2. I can ask, is A2 in the set that it got mapped to? This is a yes or no question. Similarly, A3 gets mapped to F of A3. Is A3 in F of A3? This is yes or no. So what D is D is taking all of the elements here where the answer is no. If the answer is no, if A1 is not in F of A1, then A1 is in D. Let's suppose that A2 is in f of a1, then the answer is yes. Then we're going to say a2 is not in D. And a3 is in D because the answer is no. So that's all we're doing is when an element gets mapped to a set that doesn't contain itself, we put it in D. This is a well-founded set. Just for practice, let's think about some functions and what D is going to be. So of course it depends on f a lot. So f might send, let's do some examples. What if f of a is the empty set for all a? In other words, so f sends elements in A to subsets. What if it sends everything to the empty set? In that case, our D is going to be the entire set A, right? Because everything gets mapped to the empty set, which doesn't contain it. However, what if f, let me do a different function. Suppose we have a different function, g of A, that gets mapped to the entire set. So every function gets mapped to the subset, which is the whole thing. In that case, D is going to be the empty set because everything is contained in A. Okay, so that was just a little bit of warm-up to get a feel for what D is. So it has a flavor of Russell's paradox, but there's really no paradox here, and there won't be. So what are we trying to do? We're trying to show that D, for any f, this D, which is going to depend on f, this is in the codomain, but it's not in the image. It doesn't get hit. So we will take an arbitrary element in the domain, any arbitrary element, and I will show you that f of a cannot be equal to D, which will establish that f cannot be onto. There are two cases to consider. Either A is in D or it's not. So we'll start with the first one. Suppose A is in D, which by definition means that A is not in its image under F. Okay, so before I get to this, right down here, let me draw a picture. So what we have is we have an element, arbitrary element A, that gets mapped to F of A. And remember, we want to ask, does this set F of A, again, that's a subset of A, it's in here, does this contain A? Yes or no? And the fact that A is in D, by definition, if A is in D, then A is not contained in F of A. In other words, by construction, the answer is no. So that means that this set F of A is some unknown to us, unknown set that does not contain A. What do we know? We know that D is a set that contains A. So this unknown set, it can't be D. i.e., it cannot be D because A is in D. So that's the sentence right here. F of A cannot be D because D contains A, but F of A doesn't. Okay, so in case 1, we know that A does not get mapped to D. F of A is not equal to D. Let's prove the same result holds in case 2. So suppose that A is not in D. Then by definition, if A is not in D, then this has to be false, meaning A is in F of A. A is in the set that it gets mapped to. As before I read the text that just appeared, I will explain it with a picture so it makes more sense. So we have an element A, which is an arbitrary element that gets mapped to a set F of A. And what do we know about this? So A is not in the set D. So that means that it's not one of these elements that satisfies this condition. So it has to be the case that this condition is false. So A has to be in f of A. Said differently, if we can ask, does this set contain A? The answer, survey says, yes, by definition. So now we have this set f of A. This is unknown. It's unknown to us. It's an unknown set, but we know that it contains A. Containing A. However, we know that the set D does not contain A. So it can't be D because A is contained in D. So that's what the sentence says. So this means that f of A cannot be D because f of A contains A, but D doesn't. So we have defined a set D and shown that no matter what we pick for our input, f of A cannot be equal to D. Therefore, there is no surjection and certainly not a bijection then from a set to its power set. And that completes the proof. And notice that that says that there are infinitely many infinities because we can start with the natural numbers and we can say that the natural numbers is smaller than the power set of the natural numbers. And let me call that power set, so let me call this first set A naught. And let me call this power set A1. And this is strictly smaller than the power set of A1. And let me call that A2. And this is strictly smaller than the power set of A2. And let me call that A3. And so forth. So given a set, we can keep creating power sets and get this infinite chain of infinities that are all growing in size. At last, we have arrived on the last slide, and I've been promising that they get better and better, so hopefully I can really deliver here. You be the judge. Okay, in the previous slide, I defined the cardinality of the natural numbers to be A naught, because I really didn't want to write this complicated letter. This is a Hebrew letter called Aleph. And so Aleph naught is actually the standard convention for what we call the size of the natural numbers. And we say that a set S whose size is equal to Aleph naught is countably infinite. The term countable usually means at most countably infinite. So basically it means we can count the elements in the set. Might be finite, might be infinite, but we can enumerate them 1, 2, 3, etc. That said, there are some books and some paper that say countable, that use the word countable specifically to refer to infinite sets, and they'll just use finite otherwise. If a set is bigger than Aleph naught, then we say that S is uncountable. So we have already seen that the size of the real numbers is uncountable, as is the size of the power set of the rational numbers. Okay, so this slide is called More Fun Facts, so I'm just going to list them off and go out with a bang. Fun fact number 1, the rational numbers can be covered with intervals whose total length is 1. So here's what I mean by that. So we have the real line here, and 0 here is 1, the integers, etc. But the rational numbers are everywhere. They're dense. I mean, that's actually a term from analysis. No matter where you go in the real line, if you zoom in far enough, or no matter how much you zoom in, you will get infinitely many rational numbers. I claim that somehow we can cover the rational numbers with intervals whose total length adds up to 1. And every single rational number in the entire line is going to be in some interval. Seems impossible, right? Because if you cover the rational numbers, since they're dense, you have to basically cover everything. Because how can you cover how can you avoid an irrational number? That's a good question. So it takes us back to calculus. Remember that the infinite sum from 1 to infinity of 1 over 2 to the n is equal, well, it's 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc. This thing equals 1. Now think of this as a frog that's leaping halfway to the wall, then a quarter of the way, then an eighth of the way. The total distance traveled is going to be 1. So what we can do is we can take a bunch of intervals, and so by an interval I really mean like a little chunk of the real line that has length 1/2. So take an interval that has length 1/2, take a little piece that has length 1/4. My drawings are not going to be perfectly to scale because they'll just get too small too quickly. Take a little interval that has size 1/8. Take an interval that has size 1/16. Take one that has size 1/32, and they shrink very quickly. And if I take these, well, so first of all, we can enumerate the rational numbers somehow. So we can give out name tags or football jerseys to every single rational number. So any fraction on this real line has a jersey number, a natural number jersey, 1, 2, 3, 4, one of these guys. Okay, so what we will do is we'll go to the real line and we will cover rational number 1 with this first interval. We'll find rational number 2, and we'll go here and we'll stick. So suppose rational number 1 is right here. We stick the first interval around it. Suppose rational number 2 is out here. We stick the second interval there. Rational number 3 might be out here. We stick the third interval. And for every single rational number on this line, the nth rational number gets covered by the nth interval. And these intervals are decreasing so quickly that their total sum is equal to 1. So at the end of the day, every rational number in this entire real line lies in the middle of one of these intervals. And the total length of the intervals is 1, even though the length of the whole real line in which the rational numbers are dense is infinite. That seems like it's impossible. It seems like a paradox. But mathematically, it's absolutely legit. Pretty cool, right? Okay, fun fact number 2. The set of real-valued functions is strictly larger than the real numbers. And that's actually not surprising. Let me actually convince you of it right here. So, well, first of all, for any real number, you can define a function, as I've said before, f of x equals the constant function a for any a. So there's at least as many functions as real numbers, but more so for any subset. So fix a subset A of big A of the real numbers, then define fa of x to be 1 if x is in A, and 0 if x is not in A. So these are clearly different for all subsets. And so here we have at least as many. So the number of functions is going to be at least as big as 2, as the power set of the real numbers, and we know that's bigger than the real numbers. Okay, so I should say one more thing, that the cardinality of the real numbers is actually called the continuum. So we usually denote this with a lowercase c and call it the continuum. Fun fact 3. I guess this one maybe is not quite as cool as the last two, but we can finally answer our question from the beginning of the lecture. Remember we had that chain of subsets? Now we know that the even positive integers is the same size as the positive integers, which is the same size as the natural numbers, the non-zero integers, which is the same size as the integers and the rationals, which are smaller than the real numbers and strictly smaller than the real valued functions. Our penultimate fun fact is a question of whether there exists a set S whose size is bigger than aleph naught but smaller than c. That question is called the continuum hypothesis. So in other words, is there a set bigger than the integers but smaller than the real numbers? And it's not really a fun fact by itself, but I guess a little bit of history behind it is. So Georg Cantor, remember him, the diagonal argument that we saw earlier, he spent many years of his life trying to prove this, and he would come up with a proof and then later say that was wrong and find a disproof, and he kept going back and forth, and it literally made him insane. Like, he was hospitalized. He was put in a mental institution because it drove him crazy. I don't know about the cause versus correlation of that. And this was in the late 1800s, and he never did prove it or disprove it. Much later, so we're jumping from the late 1800s to I think around 1940, Kurt Gödel, remember him? He came up in a previous lecture. He had the incompleteness theorem, which showed that there are mathematical results that are unprovable. They are outside of our set of axioms. He proved that this was one of them. Well, he proved that the negation of this is unprovable. It lies outside of our mathematical framework. And then later, in the 1950s or 60s, Paul Cohen proved the other half. He completed the proof that the entire continuum hypothesis is undecidable. It lies outside of the standard axioms of set theory, and that means that Georg Cantor, bless his heart, was spending years of his life going crazy trying to prove something that was unprovable. And specifically, that means that you can assume that it's true, and you will never reach a contradiction. And you can assume it's false, and you will never reach a contradiction. So this is probably what Cantor was wrestling with without ever realizing that there were results that were unprovable. Okay, so that hopefully is a fun place to finish. I hope you enjoyed this lecture, and we're going to leave it there.